When people hear the phrase El Nino, they often assume it means a storm that occurs once every 100 years. In reality, it means there is a 1% chance of that storm occurring in any given year. As climate variability increases and Southern California experiences more intense rainfall events, understanding how storm severity changes with rarity becomes increasingly important. My research question is, can derivatives of precipitation frequency models quantify the increasing severity of rare Southern California storms? First, I'll introduce the motivation and research question. Next, I'll discuss the NOAA precipitation data and how the dataset was assembled. Then, I'll explain the regression models used to describe precipitation behavior. After that, I'll apply calculus to those models and introduce my storm severity index. Finally, I'll present the results, discuss their significance, and conclude with my future research directions. Before discussing the mathematics, it's important to understand why storm severity matters in Southern California. Although Southern California is often associated with dry weather and droughts, the region regularly experiences extreme precipitation events. These include flash floods, atmospheric rivers, strong El Niño winters, and periods of rapid drought recovery. One of the most important contributors to these extreme rainfall events is the atmospheric river. Atmospheric rivers are narrow corridors of concentrated water vapor that transport enormous amounts of moisture from the Pacific Ocean toward the western United States. When these systems encounter California's mountains, they release large amounts of precipitation over relatively short periods of time. To prepare for these events, engineers and hydrologists rely on NOAA precipitation frequency tables. These tables provide estimates of how much rainfall can be expected for storms of different durations and probabilities. However, these tables only tell us the total amount of rain that falls. They do not tell us how rapidly storm severity increases as storms become longer or rarer. This gap motivated my research. Rather than focusing only on rainfall totals, I wanted to investigate whether calculus could provide a way to quantify how storm danger grows. Specifically, I wanted to determine whether derivatives of precipitation frequency models could measure the increasing severity of rare Southern California storms. To answer this question, I analyzed precipitation data from 5 Southern California locations and developed mathematical models relating precipitation depth to storm duration. I hypothesized that lower probability storms, such as 4% and 1% annual probability events, would exhibit substantially larger derivatives than common storms, indicating a faster growth in precipitation severity. If true, this would suggest that derivatives can serve as a meaningful mathematical measure of storm risk. This study uses precipitation frequency estimates from NOAA Atlas 14, which is the standard dataset used by hydrologists and engineers for stormwater and flood design. I selected 5 locations representing different regions of Southern California: Irvine, Fullerton, Los Angeles, Lake Elsinore, and Duluth. From each station, I extracted precipitation depths for 5 storm durations ranging from 1 hour to 60 days, and 4 annual storm probabilities ranging from 50% to 1%. This produced a dataset of 100 precipitation measurements. By averaging the values across the 5 stations, I created a regional Southern California precipitation dataset that could be modeled mathematically and analyzed using calculus. After organizing the NOAA data, the next step was to transform the observations into mathematical models. For each probability category, I averaged the precipitation depths from the 5 Southern California stations. This produced a regional dataset representing common, uncommon, rare, and extreme storms. I then used Google Sheets exponential regression to model the relationship between precipitation depth and storm duration. Using Google Sheets exponential regression, I modeled precipitation as P of t equals A times e to the k times t power, where P of t equals precipitation depth, A equals initial precipitation coefficient, k equals growth constant, and t equals duration index. Each model achieved an R-squared value above 0.99, indicating an excellent fit. After creating the precipitation models, I applied calculus to measure storm severity in a deeper way. The original model has the form P of t equals A times e to the k times t power, where P of t represents predicted precipitation depth and t represents storm duration. The first derivative is P prime of t equals A times k times e to the k times t power. I used this first derivative to create the Storm Severity Index, or SSI. The SSI measures how rapidly precipitation severity increases as storm duration increases. In other words, it tells us how quickly storm danger is growing. For instance, the 50% probability storm's first derivative at the longest duration of 60 days gives an SSI of approximately 11.038. The 1% probability storm's first derivative at 60 days gives an SSI of approximately 15.82. This means that at the longest duration, the 1% probability storm increases in severity about 4.6 times faster than the 50% probability storm. The table shows the resulting SSI values. The 50% probability storm has an SSI of 11.038. The 20% probability storm has an SSI of 19.35. The 4% probability storm has an SSI of 33.83. And the 1% probability storm has an SSI of 50.82, all values calculated at t equals 60 days. The inequality shown on the slide summarizes this trend. This indicates that the most extreme storms have the largest rate of severity growth. One important point is that these numbers are not rainfall totals. For example, 50.82 does not mean 50.82 inches of rain. Instead, it represents the magnitude of the derivative or the rate at which the precipitation severity is increasing. Larger SSI values indicate that precipitation accumulates more rapidly as storm duration increases. But I also wanted to know whether storm severity itself was accelerating, so I took the second derivative. The second derivative is p double prime of t equals a times k squared times e to the k times t power. I defined this as the storm acceleration index, or SAI, where SAI of t equals the second derivative of p of t. The SAI measures how quickly the storm severity index is increasing. The 50% probability storm's SAI at 60 days is approximately 7.1697, and the 1% probability storm's SAI at 60 days is approximately 37.522. This means the 1% probability storm does not only have a higher severity growth rate, its severity is also accelerating about 5.2 times faster than the 50% probability storm. The storm severity index helps measure how quickly storm severity increases, but it does not tell us whether that increase itself is accelerating. To investigate this, I applied calculus a second time and calculated the second derivative of the precipitation models. I defined the storm acceleration index, or SAI, as SAI of t equals the second derivative of p of t. The SAI measures the acceleration of storm severity growth. The 50% probability storm has an SAI of 7.1697. The 20% probability storm has an SAI of 13.2127. The 4% probability storm has an SAI of 24.0554. And the 1% probability storm has an SAI of 37.522. Notice the same inequality pattern that appeared with the storm severity index. As storm probability decreases, the storm acceleration index increases significantly. This means that rare storms do not simply become severe more quickly, they accelerate toward extreme severity much faster than common storms. To quantify this difference, I compared the 1% and 50% probability storms by dividing their SAI values respectively, obtaining a value of 5.2. This indicates that the 1% probability storm severity accelerates more than 5 times faster than the 50% probability storm. This is important because it suggests that rare Southern California storms are disproportionately dangerous. Their impacts grow faster and faster as storm duration increases, which helps explain why extreme events, such as atmospheric rivers, can produce flooding and infrastructure design that far exceed what rainfall totals alone might suggest. The storm severity index could be useful for flood risk assessment, reservoir management, stormwater infrastructure design, emergency planning, and climate resilience studies. Traditional NOAA tables tells engineers how much rain might fall. The derivative tells us how rapidly that risk grows. This project demonstrates that derivatives can successfully quantify storm severity. By fitting precipitation frequency models and differentiating them, I developed a storm severity index that measures the rate at which precipitation danger increases. The analysis shows that common storms increase gradually, rare storms increase much more rapidly, and extreme storms accelerate in severity as duration increases. Therefore, derivatives of precipitation frequency models provide a meaningful mathematical tool for quantifying the increasing severity of rare Southern California storms. They transform precipitation frequency tables from static measurements into dynamic models of storm risk. Thank you for listening to my presentation.